All right, let's use the rational zeros theorem to find all the real zeros of the polynomial function at the bottom there. And we're going to use that to factor the function as well. Now, remember that the rational zeros theorem tells us that our factors of the constant term over the factors of the leading coefficient, in this case 1, those are the possible rational zeros. If there are any real zeros here, at most we're going to have 3. And since rational numbers are real numbers, at most we will have 3. So I need to look at the factors of 60 over the factors of 1. And we could have the positive or the negative of that. So let's see here. Now the only factor of 1 is 1. And dividing by 1 is not going to change anything. So we get a little lucky here. We're just looking at positive or negative factor of 60. 1 in 60, 2 in 30, 3 in 20, 4 in 15, running out of space here. So we had 20, 30, and 60. 4 and 15, 5 and 12, 6 and 10, and then 7, 8, and 9 are not factors of 60. And that's plus or minus any of these. So we need to indicate to our instructors that we are aware that positive negative applies to everything. I'm going to graph this and look for some x-intercepts. So we had y equals x cubed, and if your calculator's printing this out in a pretty fashion, then scroll to the right to get out of the exponent, plus 9x squared. Oh, it didn't make an x there. X, 9x squared, minus 16x, and minus 60. Now at first, because of my rational zeros, the one with the largest absolute value is the positive and negative 60. I could look at negative 61 to positive 61 in the x direction, and I don't need to see much in the y direction, because with a 0, well, a 0 makes the function, it's a value of x to put into the function to get 0 out for y. So we're looking for y-intercepts. That's when x-intercepts, that's when y equals 0. We don't need to see too much in that direction then. Now, it would seem that the space that I'm seeing is at least too big in the x direction if I were to reduce that, say, negative 30 to positive 30, maybe cut it in half again, say negative 15 to positive 15. I'm seeing 3 x-intercepts there. So there are 3 real zeros, whether they're all rational or not. This one looks to be perhaps at negative 10. So I'm going to trace there. Negative sign. There we go. Remember, that is not proof. We need to show this by synthetic division. So let's see. We had x cubed, 1x cubed plus 9x squared minus 16x minus 60. And we are testing whether negative 10 is a zero of this function. So I'm going to do synthetic division here. Bring down the 1. Multiply the last entry in the bottom row by what's outside. Bring it up here diagonally, and then add. Watch your signs. That's a negative 1. Multiply by a negative 10. That's positive 10. Negative 6 when we add. Negative 6 times negative 10 is positive 60. I do get a remainder of 0. So x equals negative 10. That is a 0 of this polynomial function. And furthermore, that gives me that x plus 10 is a factor. When you divide a cubic, degree 3, by a linear, degree 1, what we're left with here are the coefficients of something that begins with x squared. X squared minus x minus 6. Now, there are 2 ways we could continue here. This is actually something that could be quickly factored. Since that's a 1x squared, negative 3 and positive 2 will give us a product of negative 6, and then add to negative 1x. However, sometimes we either don't see it or it's not factorable by methods that we know. And so what I'm going to do is continue with where I left off, not going back to the beginning, but taking the 1, negative 6, the negative 3 and the positive 2 that I mentioned here were in factors, so that'd be x minus 3 and x plus 2. So let's go with 3 as a 0. Test whether that is a 0. That was on the list, as was the negative 2. 1, multiply. 3, add. 2, multiply. 6, add. 0. So that's telling me that x equals 3 is another 0. I already had the factor x plus 10. In breaking down, in factoring what we started with, I didn't go back to the beginning. I worked on factoring the remaining quadratic. And so x minus 3 is a factor, and the other factor we divided a quadratic by linear. Degree 2 divided by degree 1 will be degree 1, linear. So that's 1x plus 2. And with that third factor there, we had x equals 3 being a 0, going with the factor x minus 3, we get one more 0, x equals negative 2, going along with the factor x equals negative 2. Sorry, x equals negative 2 is a 0. And x plus 2 is the factor. So this is a complete factorization, and the zeros that we were looking for are x equals negative 10, x equals 3, and x equals negative 2.